is aware of it. So let everyone exercise their choices. Okay. I hope you remember a little bit about fracture mechanics. So why don't you give me some idea about fracture mechanics? Kunika, let us start with you. Remember what it is? When there is a crack in the system, what happens? Stress intensity factor. You remember that? Kunika?
Yes, sir. There was a formula that if a
Yeah.
crack initiated grows like in a radius.
Yeah.
I don't remember the formula, but it is like something like
So that formula gives you what? That formula tells you about so relation between which parameters?
so the starting of the crack.
Starting of the crack growth.
Yes, sir.
Okay. Ishika, do you remember something?
Sir, I guess stress versus radius, मतलब कि how much stress, how the stress varies actually with that with
Yes.
that.
Yes. Yes. Yeah. That is true. And do you also remember the equation?
No, sir, I just remember it was inversely proportional to the radius.
Great. I'm happy that you remember that much. So let us revisit that. So, and then we are going to model a special type of model which we call modified. Oh, the colors are changing. Modified boundary layer model, also called SSY model, a modified SSY model, mod SSY model. This model is famous in fracture mechanics only, which is not a very big community. Nevertheless, it has its own perks. So, okay, so let us revisit a little bit about fracture mechanics. Fracture mechanics is something when we have a crack. So I will just bring a little bit history of fracture mechanics to you, maybe. So it is 10:10. I will try to finish it within 10:15. So it all started with whom? So basically, there were, if you go back in the history of science, so of course we have forgotten about what happened in the scientific process of Indian history because we have lost the meaning of the language we once used to exercise for science. Also in the Western community, Latin used to be the language, but now, and at one point of time, English took over. Still, we have the essence of Latin in science. So if you go in biology or medicine, you will see a lot of terms coming from Latin language, which makes it sometimes non-understandable. But if you know Latin, it helps to understand. So in those days, including Archimedes, if you remember Archimedes, when he tries integration, what he does is he takes a irregular geometrical object, such as a potato, and cut slices of it, and so small slices that each small slice, for that you can calculate the area. And a small thickness will give you the volume of that. You integrate the whole thing. And that's how you know the whole volume of the irregular object. So people were playing a lot with the geometrical things. So in fracture mechanics, it actually began if you have a hole in the system. If you have a hole, what happens? So then English gives stress concentration factor, if you remember. So sigma at the tip or near the hole will be having a magnified value in comparison to what you have applied on the system. So if you have applied sigma, which is sigma applied, and this is 2A. So major axis, and this is 2B minor axis. Then it will be magnified here and here. And you can find out how much magnification will be based on this equation. But what happens if it becomes very sharp? If the upper surface comes very close to the lower surface, then what is the value of B? The value of B tends to 0. And therefore, 1 plus 2A by B, so this term tends to infinity. So here only you see the signal that if this thing becomes very sharp, then the amount of stress you can feel at the tip can reach infinity. So it becomes asymptotic. And for this, you don't need Irwin, you don't need William or any other person Griffith or anyone who discovered fracture mechanics. In the solution of English, you had this already, that stress will become infinite at the tip if the crack is very sharp, if the discontinuity is very sharp. Right. So using this, when Irwin and other, by using theory of elasticity, they define if you have a crack, then what will be the stress here? So in the body, you have a crack somewhere here. This is the crack tip. And if you go away from it, whatever stress you are applying, that much amount of stress will be felt, because you are too far away from this object. And you see that forces, they somehow decrease, not in a linear way, but in a non-linear way, as you go away from the source of this singularity. So it is very similar to going away from a massive object in space, where the gravitational force decreases as 1 by r square. So there also you have a singularity, because if you make r 0, what will happen to the gravitational force? And similarly, you have magnetic force, Coulombic forces. Everywhere you know that if you go away, the force decreases, and it decreases very sharp. So when you are much away from the crack tip, then whatever you have applied is realized on the system, because you are much away from the discontinuity. If you come closer, then the stress should increase. So here the stress remains same. At some point it starts feeling the crack, and then it goes asymptotic here. So this should be the profile if you apply of elasticity. So sigma ij, it can be sigma xx, sigma yy, sigma cz, or shear stresses, whatever. All those are asymptotic function of the radial vector r and angle theta. Okay. So at any position, if you want to calculate what is the value of stress, then you need a relationship which can describe, depending upon how much distant it is from the crack tip, which is the origin, and what angle it is making in the Cartesian coordinate from the abscissa. And so with these two, you can find out the stress at different location. And this is given by expression. So basically, when you use theory of elasticity, you actually get sigma by 2 pi, and then you get a common term. So I think, so let me write it back, because I remember the final equation. So final equation is k divided by root 2 pi r f of theta, and this is, and so we have spoken about mode 1, mode 2, mode 3. That will bring more complication, but just remember that we are in mode 1. What is mode 1? Mode 1 is this. So if you have a crack, I'm pulling it like this. So this is called opening mode or mode 1. And we are going to deal with this. So this is how the stress is defined. And when you calculate stresses using the theory of elasticity, and then you have these variables here, theta and r. So you get a common term. So if you're calculating sigma xx, sigma yy, sigma cc, or other shear stresses, you get a common term in all these. And that common term is sigma root pi a. If you change it to root pi a, then root over 2 pi r. So yeah, so I'm doing a back calculation, but actually when you calculated stresses, you didn't have this symbol k. So when you calculate stress, then it all became a function of sigma root a divided by root 2r and f of theta. And because this term was constant in whatever stress function you take, they describe another parameter k, which is sigma root pi a. And then when you put this one in this equation, you get this form. So what I'm trying to say here is that k was not discovered before this expression came. And because there was a constant term in any of the expression of the stress, they defined that constant or the constant expression, not a constant variable, because it is a variable. If you change a or stress, this will change. But this expression is common in all the stress functions. So they defined this to be a parameter k, which is a stress intensity factor. F of theta will change for different directions. So f of theta will change, but this will remain same. Okay, so you again see the same thing. R goes to 0, this goes to infinity. That cannot happen because in reality you cannot have infinite amount of stress in a material. Material cannot take infinite amount of stress, because if that would have been the case, then material scientists will not have to do anything regarding the strength of the material, because it can take infinite amount of strength. So you just put a hole in the system and your material is like immortal. But that doesn't happen, and that is a different story, what happens because of plasticity. So this is the brief introduction about what we studied in fracture mechanics, and you remember this equation. But this equation, sigma ij is equal to k root 2 pi r f of theta, is not complete. You have other terms after this, and the other term, so it is a Taylor series. So you start with root r, and then the power of r keeps on increasing. And you ignore the higher order terms, but what is the second term? The next term, which is just after this, has a proportionality with r, just r. And that term in the matrix notation takes this kind of form. Okay, so we are adding just one extra term here, and apart from that higher order terms, again we are still ignoring. We are still in the safe zone. You don't have to take care of this, and a lot of many of the times you will only use this. But this becomes important if you have a system, if you have a crack in the system. Why? Let us have a very brief look on what happens in 3 dimension. So this is the crack in a 3-dimensional body. Okay, so this is the crack tip. And if you keep your eye here and you are looking like this, then you will see the 2-dimension like this. Okay, so I hope you can imagine what is going on here. So this is the 3-dimensional object, and we have a crack tip here, and then we are pulling this thing. We are pulling this thing so that I want to tear this apart. Not tear this apart. I want to pull it and break it into 2 pieces. And I should have the muscle of Thor to do it. But imagine that I have, and I do it with my hands. And while I'm doing it, let us forget about fracture mechanics. Let us forget about the mechanics of materials. Just think that the material is a very, very viscous thing. It is very viscous. and it is very viscous and still viscous. So I don't need that much amount of force to break it. But imagine that it is very viscous. What will happen? So I'm trying to break this thing. Yeah, I'm trying to break this thing. So this part will go up, this part will go down. What will happen to this part? What will happen to this part here? What will happen here? Can you imagine what will happen? Okay, so because the atoms here are at the front and they are being pulled from both direction and they have nowhere else to go, but they are still in continuum with other atoms in the material. Okay, so they don't want to break bonds so easily, right? Instead, what they can do is they can flow in the direction where, so these guys are asking the atoms to come in their direction. These guys are asking the atoms to come in that direction. So the first response would be to flow, fine, but where to flow, up or down? One atom cannot flow in both directions. So some atom will have to divide. It's not one singular atom sitting at the crack tip because our crack is not that sharp. So we are not an atomic scale sharp. So some of the atom will go up, some of the atom will go down. This introduces flow of material. Flow of material is the plastic deformation, but forget about that. There is a flow of material. This flow of material will be asking material to come in, right? So it's like an army which is being compromised at the front, and the other army. Yes, Rish, you want to say something? Shirish? Okay. So you need more people to come on the front. So more people are being called upon from the country. Yeah, this is the country, and these atoms are at the boundary, and they are being compromised. So where from the army men will come? Well, they're invited from all over the country. But on this plane, there is too much demand. So even if you have to come from here, instead of going like this, it will go like this because of the stress profile in the system. So where exactly these invitation is more? Along this plane. So on this plane, there is too much disturbance. So if you look at this plane, which is like this, and this is the crack tip. So material is being invited from this direction and also from this direction. Okay. But this length is too much. So if a material wants to come from here, it will have to cover a huge amount of distance in comparison to a material which has to come from this side. Yeah. So these material will come in more than from the back side. So this will cause a sinking of the crack tip. And you will see in the experiment that this happens at the crack tip. So it will just go in. This is what we saw also in Charpy, where we saw the lateral strain. And this lateral strain was because at the tip you have demand and the material is being supplied. And because material is being supplied more from here, this thing goes in rather than this place. Same things happens on the back side also. So you will see a three-dimensional material will have a sinking here and also on that side like this. And you will also see a backside sinking, not so much prominent like I've drawn, but you will see a sinking from the backside also. So first of all, you're pulling, and this pulling is actually working like a bending. So this is a specimen. Whether or not there is a crack doesn't matter. If I'm pulling this, okay, so what will happen after some time? After some time, it will look like this. And I'm still pulling straight, but this thing, because of its geometry, is going in bending. So you have compression here on the backside. This compression is causing the material to be pushed, and that material is coming at the crack tip. Okay. So this is what is happening. And these two material flows can be described in terms of constraint. What is a constraint? We all know constraint is that you are not allowed to do this. You are grounded, you're not allowed to do that. There are some society constraint, there are some different kind of constraint. Material has its own constraint because of mechanics. The constraint is exactly at the center. So geometrical center from all direction, that place is under too much constraint. It cannot go in left, right, up or down. It cannot decide where to go. So that is a huge constraint. And that constraint can be explained in terms of hydrostatic tension. Hydrostatic is like a pressure, and it means this thing is being pulled in all direction with an equal amount. So where will this go? Nowhere. It will have to be compromised. So if this thing is high, then material is under too much constraint. If this thing is low, material is under less constraint. When we have a cracked object, then in the cracked object, we see, and we have discussed just now, that material can come from two different directions. So you have a constraint which is in this direction, which changes from the surface. So let us say that the thickness direction is x direction, the length is y direction, and this plane where the crack grows is z direction. So in the x direction where thickness, so that's the direction of thickness. In the x direction, you have at the surface, you have zero stress because that's the surface. So how is the stress profile? Stress profile will be like this. So at the surface, you have zero stress, and as you go towards the center, you have the maximum there. Yeah, and this is happening in the x direction. So that is the profile of sigma xx. Usually in the books, you will see the nomenclature is sigma zz because they take the thickness in the z direction. So here the stress starts from zero from the surface, goes to a maximum in the center. But this is one way of looking at it. If you look it in the z direction, so from here, so stress is what sigma is applied, and then as you go at the crack tip, you have a maximum here. Yeah. So these two profiles would cause different amount of constraint, although this is a single thing. The constraint is single thing, but you can divide it. You can divide it into two effects. One effect which is coming from the thickness direction, one effect which is coming from the ligament direction. And this thickness direction thing is called out of plane constraint. Because when we deal in 2D, so this is my plane and the thickness is coming out of the screen, so which is out of plane. So we simply call it out of plane constraint. And the constraint which comes from this direction remains in the plane we are studying in 2 dimensions. So that is called in plane constraint. Okay, fine. So I hope you have a little bit of idea about what constraint and what is the importance of that. And we broke down sigma ij defining like this. So first term have stress intensity factor root rf of theta. And then there is a second term which is called T stress. I don't know why it is called T stress, but it is called T stress, and it has two components. So the whole matrix is like this. So in the thickness direction, in the ZZ direction, you have Poisson's ratio into this amount, which will be applied in the thickness direction. So that stress. And you have 1 into T, which will be coming in the sigma XX direction. So there are only two components. One is out of plane and one is in plane. And rest of the things remain 0. Okay. So this terms defines constraint. Nothing to bother about it. I just wanted to give you a brief of a second term, which is actually not asymptotic when you go to the crack tip. So using this, we have a method to define. To define what? To define that. So how can we define that? The condition is plane strain condition. So plane strain condition can be defined if this term is 0, then we are completely conservative and this term is gone. If this term is non-zero, then we are not in the plane strain condition, or that is in sophisticated way called SSY condition, which is small scale yielding. And we will not discuss this, what it is, but it simply means that the plasticity at the crack tip is very, very small. It means that when it means that when T is 0, then this happens. Okay, fine, nothing to worry about. So we assume, so after studying all this about T stress, I'm neglecting it and I'm coming back to my same equation where I don't have T stress. But why did I discuss T stress? Because how will you model something where you don't want to have constraint? So to ensure this, that this part is 0, to ensure this, you need to calculate how much displacement you should apply in order to get this term 0. So how do we do it? We do it by imagining that, fine, this term is 0. So we stick to this. We stick to this equation. Sigma ij is equal to k divided by 2 pi r f of theta. Fine. And I have imagined that there is so there is too much constraint actually. So it is a plane strain condition and small scale yielding and everything, and T stress is 0. Okay. So I have only this. And now I want to model it. How do I model it? In order to do that, I assume. So what does it mean? It means my plasticity is very, very contained. It is limited. It is not 0, but it is limited. What is not 0? Plasticity. Don't get confused. T stress is 0 doesn't mean plasticity is 0. T stress is 0 simply means that plastic zone is very small. Okay. So this is my object and I have a plastic zone which in mode 1 looks like a butterfly. And this zone is very small. Okay. This zone is very small. I need to model the whole thing and I need to find out how much is the stress and strain at the crack tip, and I want to know more details about it and a lot of complications. So if I have to perfectly model this and want to represent reality, I will have to put holes, I will have to put rigid pins inside it, I will have to define a contact between pins, then I'll have to apply this opening, and then I will have to mesh it, and I will have to control meshing, and I have to do a very refined mesh here. Okay, and there are different types of meshing schemes at the crack tip. Too many complications if I want to do this. Can I make it simpler? So instead of modeling this whole thing, I will take a small scoop of the material out from here, and I will just model that part. Okay. So I take a circular object, completely circular object out of it. And schematically, good. It looks like this. But of course, I have a crack here. Oh, it's not going away. Okay, so imagine it's not there. So I have a crack, and this is the part which I have scooped out, and I know that this is R and this is theta. Okay, and I know that plastic zone is inside this. I know because I have chosen in such a way that this scoop is bigger than the plastic zone. So the plasticity is somewhere inside. So what is happening at the boundary? There is no plasticity because plastic zone is inside. So here everything is, whatever is happening is following theory of elasticity. Okay. So very simple. It is following Hooke's law. Not so simple equation. Actually in 3 dimension you have sigma ij is equal to E by 1 plus minus 2 mu blah 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 blah. It's a matrix, and then you have epsilon ij, which is again another tensor. So we simply write it in this simple form, but you actually should know that a little bit bigger is going on. Okay, so very simple thing that we have on the boundary elastic equations valid, and I can use elasticity without getting bothered about plasticity. What do I have to follow? I have to follow this, which also comes from elastic calculation. So I know theta, I know theta meaning I know that theta is a variable and r is a variable. I know r for the boundary. Okay, so I can just measure this, the radius of this scoop I've taken. So I know what is r, and then I can systematically change theta with an interval of 5 degrees or 10 degrees, depending upon my ease, depending upon the amount of accuracy I need. What is k? Sorry, k is sigma root pi a. A I know is fixed. I'm not modeling crack growth so far. So a is fixed. Sigma I know. Okay. Or sigma I don't know, because sigma is what is being called upon. So I can ask, oh no, this is sigma applied. So sigma applied I know, and from that I can calculate k because I know a, and everything else is known to me. Okay. So from here I know a few things, but what I want to do, my aim is to ensure that this equation is being followed at the boundary. How do I ensure it? Because I will apply the displacement in such a way that it will always follow this equation. This is what I want to do. How can I do it? I know that at this boundary, theory of elasticity is being applied. So sigma ij, I will simply write as E into epsilon ij. Okay. And from this, I can calculate how much should be the displacement which I will have to apply. Okay, displacement will be a vector which I can calculate from this. And I can know that how much displacement should I apply in terms of, so because I'm modeling only 2 dimension, so I would know how much ux I have to apply, I would know how much uy I will have to apply at each point on the boundary. And if I can ensure that by applying a boundary condition in my model, then I ensure this equation is being followed in this scoop of material. And then I'm sure that T stress is 0. I'm in the plane strain condition with a small scale modeling and small scale yielding condition, and rest of the things we can go further from here. So what am I doing? I'm avoiding modeling this complicated thing. I'm taking a scoop out. I'm ensuring theoretical constraint that this is what should be happening. And by ensuring this, I will be able to model certain condition, and then I know what is happening. So I can refine it in a very small element sizes I can have, because I'm not modeling very big specimen. Okay. So this is the benefit of this. So the calculation for ux and uy is readily available. So ux, if you calculate in the way I showed you, comes out to be this. So stress intensity factor divided by 2g, g is the shear modulus, then r by 2 pi cos of theta by 2. This is small kappa minus 1 plus 2 sine square theta by 2 square theta by 2. Okay. And uy is, oh, and you have, so here you have further terms for conditions when you have T stress non-zero. So this is another benefit that you can actually define systematic values of T stresses also, but we will not deal with T stress too much. Actually none. So I will remove this part. But you can actually systematically do it. So you want to have 10 megapascals of T stress applied, you can do it by using this equation, applying exactly same amount of displacement, and you ensure the condition that this much T stress is applied. But forget about it. So we are ensuring that T stress is 0, and follow this equation for Ux, and you follow a similar equation for U5. So here you have K divided by 2G R by 2 pi sine theta by 2 small kappa plus 1 minus 2 cos square theta by 2, and another term for T stress, but that we are not taking care of. So these two equations are there. Now what to do with these two equations? Okay, so small kappa is equal to 3 minus 4 into Poisson's ratio. Okay, so this is not a very complicated parameter. It's just that it comes up in two equations, so you shorten it by writing kappa. G is shear modulus, and everything else you know. Okay, everything else is known. So how will you model it? So what will you do to ensure? So I want to have a stress intensity factor of 100 megapascals root meter applied. This is what I want. Okay. The elastic modulus, or straight away the shear modulus of the material, let's say, is 70 gigapascals. Okay. Then what else? You don't need anything else. You only need these two informations. And from this, you can calculate Ux and Uy. So you know K is equal to 100 MPa root meter, G is equal to 70 gigapascals. You know, you have this information. In order to calculate Ux and Uy, what else you need? You need theta, you need R, and do you need anything else? No. Okay, so these are the information you need. Now what we will do in modeling, we will make a circle instead of making cylindrical specimen. We will put a crack. So we will make a circle like this, and we will partition it. If you remember, how did we do partition? We will partition it at different angles. So we will partition it at theta is equal to 5 degrees, theta is equal to 10 degrees, 15 degrees, and so on. Okay, so this total is 15, this total is 10. So on. So with an interval of 5 degrees, you can partition the whole circle in different ways. So you have these nodes, okay, node number 1, 2, 3, and so on. So at node number 1, what do you have to apply? You have to apply a boundary condition. In the boundary condition, you have to provide the value of U1 and U2. These U1 and U2 will come by using these equations. So what will you do? You will make an Excel sheet, and in that Excel sheet, you will write the values of theta in radians. Okay, don't write it in angle degrees, because these equations use the value of theta in radians. So radian representation of 0 degree, 5 degrees, 10 degrees, and so on, in whatever way you have defined. Okay, so let me write another column for it. So theta in radian. Okay, so 180 degree is equal to pi. So pi by 180 into whatever value that you put, and convert everything to radian. So you have theta, and then here you can write a formula in Excel where you write Ux is equal to this. So K value is known, G value is known, R you know, because R is going to be constant. So if you are making a 5 millimeter radius circle, then R is going to be 5 millimeter. Okay, so 5 millimeter. So remember to change the units. So here You put r is known. You have to put r in meters. 2 pi is a constant. Theta, you know, theta will keep on changing. So you just take in the formula this column, this cell value. Then kappa is 3 minus 4 mu. Mu is 0.3. So take that value, and again there is only theta. So rest of the things are known. So you write a formula in Excel and you will have the value of ux and uy for each value of theta. Okay. So you have ux and uy for each value of theta. Then you have to write a code. And in this code, you will take the node numbers here. So node number 1, it will not be node number 1. So here I'm writing node number 1. In a backend, when you mesh it, you will have different noding system. So we'll have to find out what is the node number. So node number 1, you apply U1 and U2, which is coming from this Excel data. What you can do is you can do the whole calculation in one code also. So if you're using Python scripting to apply this boundary condition, you can do it by also doing the calculation in the code, or if you don't want to do it, you can do it in Excel and simply import it in Python and take the values and define as U1 and U2 on node number 1, U1 and U2 on node number 2, and 3 and 4 and so on. Okay. So this is how you will apply boundary condition. There is no other boundary condition you have to apply, but you can be very much simpler. You can actually model a half circle. Remember, our crack is very sharp. So we will not model this kind of crescent kind of thing. We will model the half thing and we will apply Y symmetry on these nodes or whatever axis it is. So if it is this X, this is Y. So then you have to apply Y symmetry here. Partition it at different angles. Find out the node numbers. And on each node, maybe write a for loop. And on each node, you apply U1 and U2 coming from these equations. Okay. So this is what you have to do. And then you will run the job. So material property will remain same, what we have used in the tapered bar and what we have used in the other models, 3D tensile or fracture. So the material property will remain same. Plastic data, elastic data will remain same. Don't get confused. What is that in chat? Sir, the windows. Oh, this is the old one. Okay. So don't get confused. We are assuming, and we are very correct in assuming, that on this boundary elastic deformation happens only. But there is a plastic zone also inside. Okay. And therefore, we need to provide the plastic data in the model. Otherwise, we will have no plastic zone. Okay. So is this understood what you have to do? Ishika? Sleeping?
Yes, sir. No, sir, no, sir.
So did you understand anything?
Yes, sir. I showed the boundary conditions and how you have to apply.
Yeah. So Monday you should try. So Monday there will be this thing which we will be doing. So Monday you must try making this. It is very simple. We have to model it in 2D. Everything remains same. So 2D, deformable, material property, making section, assigning section to the material, that part is done. Go to assembly module, import it as an assembly. Then go to interaction module, do nothing there. Then you go to boundary condition module. And here, even if you don't make circle, whatever, you have something in the module, just apply a boundary condition of U1 and U2 at somewhere and record it using the macro manager. So that will give you a code already written how to apply U1 and U2 on certain node. Okay. So my suggestion would be that you make this part and mesh it, and then take the mesh in the assembly and apply boundary condition there. Because if you take the object, then the boundary condition will be applied on the object somewhere. If you put it as a mesh, so if you make it dependent, mesh it in part, then apply, then the boundary condition exactly will be applied on the node. Okay. How will you find out that on which node you have to apply? You can have different ways. What you can do is you can find the node by coordinates, and you know where exactly these nodes has to be, because if you know that this is 5 degrees, where exactly this point will be. So you know the coordinate of that point. Other than that, what you can do is after meshing, you can actually see what is the node numbering Abacus has done, and Abacus will follow a rule always on the boundary. So you will have an ordering of node, and this will change for different people. So you need to ensure. So maybe this node starts at 1, and then 102, 103, 104, and so on. So then you have an array in which you have the node information 101 and 110, maybe 150. So these are the nodes where you have to apply U1 and U2. So write a for loop that for node number 101, apply U1 is equal to this, U2 is equal to this, and so on. Keep on repeating, change the value of n, do that, boundary condition is applied. So once you have written that code, run that script in Abacus, so that boundary condition is applied, then run the job. We will see, this is how it should be done. We will see on Monday, okay? If you have any question, you can ask. Have some time, approximately 7 minutes or so. No question, Kunika? Any question?
No, sir.
Suraj,
No, sir.
Ishika, Bala, Shirish,
Yes, sir.
बोलो क्या क्वेश्चन है? Shirish, Shirish,
Sir, your voice is breaking.
my voice is breaking.
Yes, sir.
So I'm saying, if you have any question, do you have any question?
No, sir.
Naga, you have any question?
No, sir.
Okay, then all the best
Sir,
with others.
I have
Yeah?
one question in MM304, sir. Like
Yeah?
hysteresis, सर हिस्टेरेसिस लूप से यील्ड स्ट्रेस कैसे निकालें? जहां वो स्ट्रेन जीरो हो रहा है वो यील्ड स्ट्रेस होगा या
नहीं,
और
yield stress, see, hysteresis loop is actually two stress strain diagrams.
Yes.
One stress strain diagram in tension and another. So if it is tension cycle, if it is tension compression cycle, then you have a stress strain diagram in compression. So ऊपर वाला पार्ट को अलग करो और उसको स्ट्रेस स्ट्रेन डायग्राम प्लॉट करो, फिर उसमें 0.2% पे इंटरसेप्ट काटो पैरेलल लाइन से, जो तो वो जहां पे इंटरसेक्ट करेगा that will be your yield strength. So in one hysteresis loop you will get two yield strengths, one on the upper side, one on the lower side. Yeah.
Okay, sir.
And in compression, if there is a Boschinger effect, so some dislocations are working when you're applying, let's say, stress in one direction. So dislocations are moving in that direction and they are getting locked and a lot of things are happening. So dislocations are locked. When you reverse the direction of the stress, these dislocations were locked. For instance, when you have to go from Roper to Chandigarh, that is the direction you are applying stress. So these cars are jammed in traffic. And then you reverse the direction. So the back side, there is no jam. So some of the dislocation will go freely. So you should have yield strength smaller in the reverse direction, which is called Boschinger effect. So we will see in the results if you find something or not. It depends on material if you have this kind of effect or not. So we'll see that. Okay.
Okay, sir. Yes, sir.
Okay, all right, then see you on Monday, and hopefully we will do some simulation then. And probably the next week will be the last week for our modeling simulation, and after that we will have an examination. So you must be prepared in the week of 22 and the week of 29th. So the week which starts from 22nd and the week which starts from 29. You should be prepared in these 2 weeks. It would be better if you can give me a date for doing Viva for these 2 labs. If you don't give it to me in the next week, then I will be just deciding and I will ask you to come for the Viva. Okay?
Sir,
Yeah.
the one sheet you have shared, sir, that have
Yeah.
results. So, sir, the machine does not give the strength of both, like compression or the tensile expansion, sir.
Come again, I didn't get it.
So the machine does not give the value of two yield stress in both the cycle, the upper and the lower.
Okay, it is giving one value.
What then it is what's the average of both the values?
No, no, no. I'm asking the data has any value of yield strength already in it.
Yes, sir. It has 0.2% yield stress value and 0.02% yield stress value.
And what have I asked? Have I asked to calculate yield strength for all the cycles?
10 cycles, sir.
10 cycles. So for 10 cycles, you calculate 2 yield stresses for each cycle 2. So per cycle 2 values. Okay.
Okay,
So
sir.
if you are very sure that whatever is given in the data is correct, then you need to perform only for the reverse one. Okay. And if you really believe that you can be instrumental and you do not believe the data and you want to check it, then you can perform for both cycles.
Okay, sir.
Or you can write a code. You can write a code for drawing a line. So let's say 10 data from the initial curve in a range of 100 to 200 megapascal, because there the slope will be linear. It will be in the elastic range. So when the stress value is between 100 to 200 or 200 to 400, in that range, select some data and fit it in a linear fit, find out the slope of that. Once the slope is known, draw a parallel line at an offset of 0.002. So you know the intercept value, you know the slope value, draw a line y is equal to mx plus c and find out the interaction with the curve. And then you know what is the yield strength. You can write this code. Okay, do it in whatever way you find it easier.
Okay, sir.
Okay, all right then. See you on Monday. Bye.
Thank you, sir.
Thank you, sir.
Okay, thank you all. If you want to end the call, stop recording first. Okay.